Hello friend, we are continuing with part B of our question. I'm going to share the link for part A in the description of this particular video so that you are able to follow up from the question. So now let us look at part B. If we have an external load of 15 kilonewtons applied to the system, then each member will take a proportion of the total load. We said the bar is composed of brass members, two brass members holding aluminium in between of them. So if the combination take a load of 15 kilonewtons, which is compressive, then we want to look at the force in aluminium and force in brass. Now, force in aluminium is given by this formula because we know this is a compound bar, and therefore the proportion taken by one of the members will be the modulus of elasticity of that member times its cross-sectional area divided by the product of the modulus of elasticity of the product of the modulus of elasticity and the areas of the respective components, then times the total load which the combination is carrying. Therefore, total area for brass is going to be because it is rectangular, it is going to be like length times width. And because brass they are 2, we are going to multiply by 2. So that becomes 50 out of 1,000 converted to meters times 12 out of 1,000 converted to meters times 2, which would give you 1.2 times 10 to the power negative 3 square meters. Now when you substitute in the value also for aluminium, because it is 1 in between the two brass members, then it will be 50 out of 1,000 times 12 out of 1,000 times 1, which will give you 6 times 10 to the power negative 4 square meters. Now what about the force or the load taken up by aluminium alone? Using that formula above, we just substitute in the values. 70 giganewtons per square meter is the modulus of elasticity of aluminium times the cross-sectional area of aluminium times the total load, which is 15 times 10 to the power 3 newtons, divided by 70 exponent 9 times 6 exponent negative 4 plus 100 times 10 to the power 9 times 1.2, which is the area of brass, times 10 to the power negative 3. Solving this would give you 3889, which will give you actually 3.89 kilonewtons. That is the force in aluminium, or the force or the load taken up by aluminium, which we can simplify by calling it FA. Now, if we just use equilibrium of a system, we can just simplify our system as this is the load which is compressive on this combination of the bars. If we know the force taken up by aluminium, then we can know the force taken up by brass. Therefore, it means force in brass is going to be the total load minus the load in aluminium, which would give you 11.11 kilonewtons. Therefore, the force in brass will give you 11.11 kilonewtons. Therefore, the load taken up by brass is 11.11 kilonewtons. Now, what about the stress in aluminium? Stress in aluminium will be the load taken up by aluminium divided by the cross-section area, which gives you 483.3 Newton per square meter. That means if we say this is sigma A in aluminium, but as a result of that external load applied, it will equal to 6.48 mega newtons per square meter. We proceed and find the stress in brass. Stress in brass, therefore, will be load carried up by brass divided by the cross-sectional area of brass, which will be 11.11 divided by 1.2 export negative 3, and this gives us 925,9258.33 Newton per square meters, which gives us 9.26 meganewtons per square meter. Now, since this load is compressive, the stress in aluminium will also be compressive, and this one in brass will also be compressive. So now we must also note that these stresses, the ones calculated above and in here, represent the changes in the stresses owing to the applied load. The total or the resultant stresses owing to combined applied loading plus temperature effect are therefore obtained using superposition. In other words, we have to combine the stresses due to the different effects. For example, due to temperature and due to the load that was applied. Therefore, if we calculate the stresses in aluminium, and if we indicate it as sigma A, it will equal to the sum of the algebraic sum of the stresses due to temperature and those due to the load. And if we are to substitute in these stresses, this will be 6.64 plus, this will be, remember these are compressive, so it will be negative plus negative 6.48. This is 13.12, which is negative meganewton per square meter, or just 13.12 meganewton per square meter, and it is the compressive load. How about stresses in brass? These are going to be, this is 3.32, which is tensile, plus 9.26, which is compressive, and therefore the answer becomes 5.94, which is negative meganewton per square meter, which gives you the stress in brass to be 5.94 meganewton per square meter, and this is also compressed. Thank you so much for watching. Follow us in our next